Welcome to the Consultants Network of Long Island. Tonight's presentation, Pro Audio from Idea to Production, given by Peter Swann. Peter Swann is a mediator, arbitrator, and litigation strategy consultant at Convergent ADR and former chief judge of the Arizona Court of Appeals. He holds a Juris Doctor from the University of Maryland School of Law, graduated first in his class out of 262, and a Bachelor's of Art, Rhetoric, and Economics from UC Berkeley. The kind of person who doesn't do anything halfway, Peter has spent decades pursuing a parallel passion, chasing a specific sound he couldn't find in any modern audio equipment. Without a single engineering degree, he taught himself electronics, product design, and manufacturing, and built two companies around it, launching Useful Arts Audio in 2016 and Neoden USA in 2017. Ladies and gentlemen, I give you Peter Swann.
Well, good evening, everyone. I have to say, especially after that intro, daunted because this Zoom meeting is full of people who have superior credentials to me in at least some form of engineering, and I don't want to pass myself off as expert of the academics of engineering or a broad spectrum. What I do is devote a whole lot of time to perfecting tiny little niches that are meaningful to me and meaningful to the people who buy the product. So I hope this story is interest to you as possible. I hope that you will interrupt as much as possible, ask questions. I don't need to wait till the end to be steered in a certain direction. So we are here primarily using this little guy. This is what's inside the Hornet, sort of an object lesson in design considerations and what it takes to actually get a product to market at a price people can afford. I should make a few disclaimers up front. This is a recognition that all life is at some point analog. When it goes into a computer and when it comes out of a computer, so long as we're still using our ears and not implanted digital interfaces, we are going to be dealing with analog. So Useful Arts Audio focuses entirely on front-end gear that digital can't replace because we're dealing with basically signal strength. Digital converters can be made to be excellent, but they can't measure microvolt differences, and they need certain voltage levels to function properly, just like the old analog tape recorders did. So all of this is an effort to give a digital system the very best data it can have and not try to fix flaws in signal quality using digital techniques. Get it right the first time, and your creative tools will do much better for you. Pro audio is, I think, short for professional audio, but in my world, what it means really is production audio. It is not hi-fi. It is not about professional listening or listening environments or listening equipment, any of that. People have their own preferences as to what sort of things they listen on. That's fine. My concern has always been with how do we get the very best sound to tape or very best sound into converters so that we are honoring the work that musicians do. So begins the story of the Hornet. When I started Useful Arts, I started it as a tube audio company. Everything was vacuum tubes, and we'll get into what the inspiration was for that. But I was trying to do tubes in a modern way using modern components and modern manufacturing techniques so that I could, again, make the product affordable. This is a purely solid-state product that we're going to be talking about, but all of them are done on Neoden machines using surface mount technology to the maximum extent possible. The Hornet, as you see, is a single circuit board contained in a box made for a guitar pedal. It is not a rack mount $3,000 expensive unit, although I do make those. It is designed to be accessible to absolutely anyone and to sound better, or to give you better capture of the sound you're getting from your microphones or instruments than pretty much any large-scale preamp can give you. And to give you an idea, behind me is an SSL 4000. It's a very well-known console that's probably mixed more hit records than any other console in history, and back when it was made in the early 90s cost the equivalent of about $1 million. Console has the ability to plug microphones into it, obviously, but you'll find that most engineers do not use inboard pre's. They use outboard pre's. Why is that? It's because an outboard pre is one of the most effective means you have of controlling the overall quality of signal without modifying the signal in drastic ways. A novice will immediately look at all the knobs behind me and say, ooh, we got to turn EQ knobs. We've got to add compression. Every time one of those knobs gets turned, we're harming the signal that came in. Now, it's not to say that those can't be used as creative tools, but the beauty of a preamp is that it gives you a real subjective experience of the signal that can't be replicated in the digital domain because, again, we're talking about amplifying a signal that's tiny, can't be replicated effectively with analog tools like EQ. Field full of intangibles. And one of my main themes that I would love to have a discussion about this is electrical engineering is based on principles, measurements that are sort of standard to the discipline, but don't necessarily capture every nuance of the output signal. We can measure things like noise. We can measure things like distortion, although we have to then define distortion as harmonic distortion, intermodulation distortion, crossover distortion, clipping distortion. And I don't think that the math that we've developed to explain how to make things work necessarily captures the subjective experience of what the output signal feels like to the listener. Pick your favorite record. We all know what it is to hear some magical sound that sucks us in a way that few others do. Is that all the gear? No. But the gear sure helps. The gear inspires, emphasizing design considerations that create a subjective experience that can't really be described with a simulation or a measurement. A simulation or a measurement will tell you if the circuit's going to work. It will tell you how much gain you're going to get. It will tell you roughly where the pitfalls for distortion and noise are, but it doesn't really explain why it is that some preamps or amplifiers instantly make people smile and some make people shrug and move on to the next stage of the process. And then build a board later on a Neoden 10, a bigger pick-and-place machine than was demonstrated last time, to show you sort of how the manufacturing process is integrated into this. All of this is heavy DFM and was before I knew what that term meant. One thing I knew when I started this company is I was not going to be able to afford to build 10,000 of them with a contract manufacturer. This was going to have to be done in-house, and it was going to have to be done with a small number of people with as much automation as possible, even though ultimately everything is hand-built.
Greatest simulation in the world electrically. It's just not going to tell you what it's going to sound like.
When I'm designing, I definitely use simulators, and they give you all sorts of useful information, but they're information geared toward the sort of mathematical models that we have. And the mathematical models that we have are the most useful for general purposes, but they don't necessarily capture that subjective experience. I mean, why is it that your pipe organ sounds magical and that if you put a certain microphone on it, it's going to put a chill down your spine? And we can talk about harmonic distortion, and I will, but that's only really part of the story. There's a lot of math that I don't think we have developed for how we deal with transients, for example. Try and get a simulator to show you the difference between a parafeed outfit with an inductively loaded tube and a resistively loaded tube. It will tell you that the tube's going to function, but it's not going to tell you why one sounds like Carnegie Hall and the other sounds like a 70s drum room. That's not a fault of the simulators. I think it's just a fact of life that we develop these mathematical models to evaluate circuits, give us some information, but that information is incomplete. You heard a little bit about my bio. A lot of it has nothing to do with engineering, but before I could walk, I was at the UCLA Film School in studios, and the gear just became part of my being. I had my head inside recording consoles before I was eligible to get a driver's license, rebuilt an old Fairchild console in the 80s, everything by stripping them apart and putting them back together again, modifying them, and then buying all the gear that was on the market in hopes of capturing a certain aesthetic that's important to me. I did that and started building very, very small volumes of tube preamps. Once I got a distribution deal and realized that I was going to have to make these things in more quantity, I kind of panicked and realized, oh boy, I can't sit there with a microscope and a tweezers and put SMT on boards if I'm really going to do this effectively. I need a pick-and-place machine. I went online, and there wasn't much out there except the Neoden machines that were well reviewed on YouTube, but you really didn't know what you were getting with this obscure Chinese company. Eventually, after talking to the salespeople, I PayPal'd $10,000 to a weird Yahoo address blind hope. Lo and behold, 4 days later, this beautiful pick-and-place machine shows up on my doorstep with absolutely no instructions or any hint as to how to operate it. So I wound up texting with the folks at the factory night after night after night until I got good at it. That led to my getting to know those designers who reminded me sort of myself. They were young people who were just passionate about this one narrow activity, developing machines for SMT assembly from their own ideas, their own technology. We became friends, and Neoden USA was born, and now we sell these pick-and-place machines to everyone from government laboratories to guys in their garage. I guess I was lucky to have been born when I was in the 60s, and we have a question, what is SMT? Okay, and I appreciate that because I never know if I'm aiming in the right direction. SMT is surface mount technology. Let's take a look at this board. We've all seen components like this, these electrolytic capacitors that are through-hole capacitors, these trim pots and things. If you see that chip there, that's a through-hole part also, meaning the components have leads, they have wires, they go through holes in the circuit board, and they're soldered in there. If you're over 50, that's the way everything was made as we grew up, with through-hole components into circuit boards. It's totally reliable, not impossible, but difficult to automate for assembly. And the components tend to be larger and more expensive than surface mount components. So let me flip the board over, and you will see lots and lots of little tiny components that are soldered to the board directly because they are literally placed on the board, on the surface of the board, into a solder paste that has been stenciled onto the conductive pads. The pick-and-place machine places all of these components very rapidly, and then the solder paste is just sticky enough to keep them from falling off while they are transferred to an oven. And this is sort of a belt-style oven. If you put a board on using a fairly precise temperature profile, melt that solder so that all of the parts are soldered at once onto the board, and you have pretty much a working product just dropping right out of the oven. In the case of this product and many others, there are still a few through-hole parts to be put in afterwards. These push buttons, for example, don't really work well in an oven. Transformers like this don't work well in an oven. So we can't use surface mount for everything, but vast majority of electronics today are all assembled with surface mount components, and that is a big driver in my design considerations, is how can I maximize the number of surface mount components I'm using so that I can automate the assembly to the greatest degree possible. Far more important than the cost of a component is the cost of a human minute. A lot of these components can often be less than a tenth of a cent to buy. You can buy 5,000 resistors for $7. It's amazing. But you still need to put them on the board. You still need to be able to make sure that they're reliably placed, reliably soldered. That's an art unto itself these machines help us with. I was born in 1965. At that point, there was barely stereo. Might have had 3 tracks, like Motown recordings were done on 3 tracks. But it was pretty basic, and pretty much anything that happened in the room went on the record. If you ever want an example of this, just a stirring example of a musical performance like this, listen to the Tony Bennett song, If I Love Again. That was done with just 3 microphones onto 1 track in the studio. And as the orchestra performed and he belted out this song, what came over the monitors during the performance while the record light was on is identical to what you hear on the record. Why? 2 reasons. Number one, there was no choice. They didn't have the equipment to really mix or process or do anything to the recording at that point. And 2, the barriers to entry were so high to become a recording musician that you got really good people who were capable of these amazing performances on a first take. That to me is very, very compelling. Not to say that I don't like heavy multi-track productions, Dark Side of the Moon, Bohemian Rhapsody, recordings that take advantage of all the technology of the day. But the lesson was that with no technology, you should be able to capture a performance that sonically send the listener into nirvana. Late 60s, we get 2 to 4 tracks with Sgt. Pepper's, you may remember. Early 70s, we're working up to 8 to 16 tracks. By the mid 70s, we've got 24 tracks. And now it's unlimited. We don't even think about it. Our computer can handle as many as we want. The console behind me is short-loaded with 48, but could handle 64, and they make this console 128 different channels. Yay! Is that really advancing the sonics? No. It advances workflow. It advances freedom to mix various elements. So there's a lot of creative freedom for the musicians. But is it making anything sound better? I submit that it's not. The real question about whether something's going to sound great happens at the very beginning when the performance is happening, and the object is to capture it as well as you can. We all start somewhere. Well, that's me in the early 80s, starting somewhere. I created a guitar amp. I've got to say, it's the best sounding guitar amps I've ever heard, except it was totally impractical because it weighed 150 pounds, because there are all sorts of design lessons to be learned. This is what really started me off. If any of you remember Chet Baker, listen to his vocals in those 1950s recordings and tell me if any sound you've heard is as intimate and compelling as that vocal sound. You can hear the spit on his teeth as he sings. It is so real. It's as if he's singing only to you. That happened in part because he was a good singer. It happened in part because he was using great microphones. Today, the microphones you'd pay $40,000, $50,000 for were available then for about $600. Great microphones abound back then. But you know what they didn't have? They didn't have brand name signal chains. They didn't have brand name preamps. You can't go back and say, well, I want to use the same preamp Chet Baker used. What they plugged their microphones into back then was homebrew gear. People's best effort to create high-fidelity sound when high-fidelity sound had existed for maybe 10 years, maybe a little less than that. They had only tubes available to them as amplifying devices, and they just did the best they could. It happened to be brilliant. I'm not just somebody who idolizes the past to idolize the past. It's a happy accident that some of that early technology contains flaws that to our ears sound magical. So I set out to find that sound. How did I do that? I confined myself to only the reference materials that those engineers would have had at that time. Read the RCA Radiotron handbook. I read the books put out by the U.S. Navy, early works on electronics that were in-depth, but also fairly primitive because discipline had only been around for a couple decades at most at that point. I wanted to work within those constraints so I would start to think the way they did and create that kind of sound. Then, of course, I wanted to add nice, clean, regulated modern power supplies, things that make devices legal today, legal to sell, all those things. Plenty of good things that happened in electronics since then. Component quality in general has gotten much better. The quality of resistors, capacitors, things like that has gotten much, much better. So how do we combine the best of modern technology with those limitations that actually created such a beautiful sound? That's how I started out doing tubes. It's a little bit of my philosophy of recording, which is that now that everybody can make an album on their laptop, everybody can get distribution on Apple Music or Spotify. Ask yourself, have things gotten better? I don't really think they have. I think that we used to have a real sense of community built around our radios. That's how we found out about music. And as music moved through society and moved through phases of popularity, we all experienced that together, and it gave us common memories, common feelings, all sorts of stuff that's lost today as we get our individualized feeds of music created from the same loops that Apple sells. Nothing wrong with that. I enjoy that music sometimes, but I think we're missing something by the ease with which we can create something that sounds sort of credible. But ask yourself, does that stuff ever sound magical? I don't think it does. Bottom line here, the subheading, how do we use sonics to translate the intimacy of a human performance is really, I think, what it's all about. Ultimately, what I'm talking about today is a product that adds 10 to 60 dB of gain to a signal. It's not that exciting a concept, and it's been done for 100 years. So why is it still something worth obsessing over? Because that 60 dB of gain doesn't really tell the whole story about what's happening to your signal. It is a trivial matter to take an op amp and get enough gain from a signal to make it usable by other gear. Sure enough, I'm talking to you right now on a mic pre that probably costs 2 cents, has amazing specs, and you won't hear any flaws. You don't hear any noise. You don't hear any hum. You don't hear any distortion. It just sounds right. And it's also totally uninspiring. If you made an album on the system that I'm talking to you on now, it would sound really, really sad, even if the performances were great. Not because the specs are bad, the specs are great, but because the soul is missing. The unmeasured part of what we do is missing. So I begin with distortion, and I'm going to talk right now about harmonic distortion, which means the addition of multiples of the input frequency to the output signal. There are many other kinds of distortion, as I mentioned before. There's crossover distortion, which I hate, and that is a byproduct of using so-called push-pull or differential circuits, where one device is handling the positive half of a waveform, another device is handling the negative half of the waveform. Very efficient, ubiquitous, can be implemented really, really beautifully, but still has a different character than what's called a single-ended circuit, which uses one device to handle the entire waveform. By using one device to handle the entire waveform, we burn way more energy than we need to. We make the device hot, and we're opening ourselves up to all sorts of sensitivity to power supply noise and other problems that differential circuits solve. But there's a certain purity, a certain magic to the single-ended circuits. And if you go to the audio files out there, you will find people who obsess over single-ended tube amplifiers that put out like 3 watts. But they do it in a way that sounds pretty beautiful. Philosophically, I prefer to do that on the production side and not alter the output of the artist with my playback system. But the point remains that a single-ended circuit, whether done with tubes or transistors, has the ability to capture sound in a way that a differential circuit does not. Everything I do is single-ended for that reason. But for all of the design challenges that single-ended circuitry presents, I think it creates something really beautiful. The first device that mankind came up with to amplify an electrical signal was vacuum triode, which has a flaw as it is driven. The cloud of electrons that allows that tube to work is not constant, and it almost mechanically duplicates what a Fourier transform will tell you second harmonic distortion looks like. You'll see in the tab 3 here on this slide something that I always found fascinating, which is that the brain does not identify a pitch by its fundamental. When you hear an A440, you're hearing the 440 for sure. That's the main thing you're hearing. But the way that your brain identifies that as an A is primarily through 880, a integer multiple of the fundamental frequency that works with our neurological development. It happens that we are wired as humans to appreciate subtle addition of harmonics into sound, and that can be a very compelling thing. The beauty of second harmonic distortion is a second harmonic is always an octave above the fundamental. It is always musically related to the fundamental. So if you artfully apply second harmonic distortion to a signal, you can create an aural illusion that basically tells your brain to pay more attention to certain signals. And that's a very useful technique when you're producing music, because you can select which signals are going to come loaded with this sort of audio MSG, makes the brain pay attention.
How do you accentuate a second harmonic without also accentuating all the odd harmonic sounds?
Aha! It's a fantastic question. I will tell you this. I've only been able to accentuate pure second harmonic one way, and it is not in the Hornet. The way that I've been able to do it is with EF86 pentode tube wired in a very cold configuration, loaded just properly. I can get that to be pure second harmonic, unmeasurable higher order harmonics, and then I strap that in parallel over the signal bus and blend it in. The color control on my tube pre's allows you to blend in pure second harmonics over a fairly small range. I mean, we're not talking massive distortion here. It's inaudible as distortion. But I've done thousands of demos of this thing where people turn a knob and you always know exactly where they're going to start smiling. There is a psychological effect that comes from the addition of these harmonics, and right around where I have it at number 6, the effect becomes so powerful that anybody, whether they have trained ears or not, will notice it. So that pentode configuration happens to be really good at it, even though the literature will tell you that pentodes generally are more inclined toward odd order harmonics and triodes toward even. I have found that this pentode does that. With the Hornet, the solid state circuit that I sell, I also generate harmonics, but you are correct. There's a ratio of second to third. I am able to stay away from the higher order harmonics, which almost universally sound nasty. But second and third can have real uses. Tape gives us a predominantly third harmonic distortion, and that's a sound that a lot of people love. Vinyl gives us a mixture of second and third, and actually quite a bit of it. It adds about 1% THD to the signal. And I think when people talk about the warmth of vinyl, how everything sounds better, what they're really doing is applying an effect, adding second harmonics and a little bit of third, that is very pleasing. And maybe more so than the artist intended. But I digress. The second harmonic is sort of a magical thing that can only be created in the analog domain with great difficulty. I've only found one way to do it. In the digital domain, I'm not aware of any digital processing units that do that. The problem with doing it at that point, though, is that you've already captured the signal. It's already too late. And there's an old adage in audio production that fixing it in the mix is not a thing. It's sort of a crutch that people hope will work, but it's never as good as getting it right in the first place.
When we're talking about second harmonic in audio, is it like regardless of the level of audio that gets inside, you generate a second harmonic, or at certain level that starts to kick in?
Excellent question. The answer is the former. It is at any level, the way I do it.
Oh, phenomenal.
It is possible to generate some of these distortion characteristics by overdriving a component. I think kind of a cheap way of doing it. The extreme example, of course, is a guitar amp that can distort like crazy just because you apply overdrive. But your question is absolutely spot on. In my pre's, that is done in the very first gain stage at a signal strength of around 2 millivolts. And that's why it's different from digital, because you can't work with a 2 millivolt signal with an analog to digital converter. You need about a volt to get full range. This pyramid, to me, describes the order of importance of various elements in a production. The performer is obviously the most important thing, the performer's instrument as well. But the room is going to be more important than the plugins and the effects units. The microphone is going to be more important than the preamp. And on you go down the pyramid and you see things becoming less and less important to the sound. Now, of course, people will always debate, the distribution medium, vinyl versus CD, things like that. Whatever part of the process is accessible to them sort of becomes the most important psychologically. I think if you really break it down and go through the whole process, you'll find that there's some truth to this pyramid. How do we define good? I always start with the power supply. That is the output of an amplifier. You're using the input circuitry to modify the power supply. You're not really amplifying the input signal. With all of my power supplies, there is at least a linear component if they are not entirely linear. With the Hornet, which is a $300 mic pre, we had to make some compromises. So that uses a 48-volt wall wart that is then processed to death with linear regulators, capacitor multipliers, every trick in the book at the analog linear level to make sure that we're getting as clean and low impedance power supply as possible out of a cheap wall wart. Headroom is something I can't underscore enough. One of the great limitations of equipment these days is that most of the op amps in audio equipment are designed to run at a total voltage differential from the negative supply to the positive supply of 30 volts or maybe 40 if you're lucky. Mathematically, that should be just fine, right? Because all we're trying to do is produce a volt or two, so that should be plenty of headroom. But when you find products that can't really produce a wave that is hotter than 15 dBu, you know that you're going to run into some really bad sound. It's going to sound like somebody's got their hands around the throat of the system. This is the same principle, I think, that leads people to debate whether ultrasonic performance is important. Can we hear 60 kilohertz? Well, no, we can't hear 60 kilohertz. But the importance of having an amp that can be flat to 60 kilohertz, the importance of having an amp that can put out plus 26 dB signal is we're taking all of the problem areas where performance starts to diminish and moving it to an area that we'll never use. meaning that the area we do use is getting the very best of what the circuit can deliver. So lots of headroom built into this. And yes, it can output plus 26 dB with no problem at very low distortion. Input circuitry, obviously we have different impedance requirements for microphones and inputs. Microphones require a fairly low input impedance. Instruments, I make one sort of exotic tube DI that has a 20 megohm input impedance. Those all get designed in from the get-go. Now, part of the history of this design, and one of the things of interest to any engineer, is I designed this circuit around certain components. And then I realized that I had made mistakes, and I had to change that. The output transformer here, this little guy here, is a wonderful output transformer with perfectly adequate headroom and a great frequency response. I was going to use it as the input and the output transformer. The problem is basically functions like a massive antenna for signals in the room. So it's sort of like having a single coil guitar that you're plugging your microphone into. And guess what? It just sounds like buzzing and humming. It's horrible. It was unusable. So I had to rethink that. That led to the development of this little guy, silver transformer, which I designed with Dave Guerin at Cinemag in a humbucking configuration to eliminate all of the 60 and 120 hertz hum that exists in the environment around us, and it worked like a charm. 1-to-1 ratio, doesn't load down the microphone, allows the transients to come through, and then I use the solid state electronics for gain. 60 dB is a pretty good gain spec, so I wanted to make sure it had that, but I wanted to make sure also that no stage was being asked to generate more than 15 dB of gain. Back in the day, in the 50s and the Chet Baker days, 3% harmonic distortion was considered pretty good, because if you were working tubes hard, you were going to get that level of distortion. Today, you get distortion as low as you want out of a mic pre on a chip that you can buy for $4. And most of the interfaces and prosumer audio production devices that you're going to have microphone jacks that go straight to a mic pre on a chip, and they do a fine job of telling you what the microphone did, but they do absolutely nothing for the audience's emotional reception. In between there, somewhere between 0.2 and 0.6, if you're really talking about the lower order harmonics, is where I find that people start reacting. So I build these things to create that and do it variably. What we're trying to do is a 1,000-fold increase in signal voltage. If we were talking about driving speakers, we'd also be worried about amplifying current. I think preamps need to worry about that also, but unfortunately, that is a design goal that's been lost. Back in the 50s, it was a design standard that every preamp had to be able to drive a 600 ohm load, which is a pretty heavy-duty load. You're asking the circuit to do a lot of work to put clean signal into a 600 ohm load. Today, almost nothing has heavier load than about 10K. You find that designers have left that standard behind and get away with using devices capable of putting out considerably less output current. I don't do that. Adhere to the old standard. Anytime you load a signal, you're asking it to do work, and not to get too exotic with physics, but Heisenberg had a point. We do alter a signal when we measure it, and so I want to make the signal as robust as possible, and that's why we have not only voltage gain, but current gain in the Hornet. Signal chain here is really fairly simple. For those of you who remember the tape days, we used to take a microphone, put it into a preamp, and the preamp would drive the tape electronics, which were themselves power amps powering electromagnets. Now we drive analog to digital converter, which is essentially just measuring voltage, not current. It requires a lot less work from the preamp, but nonetheless, it does load it down a little bit. Beefier you make that output signal in terms of current, the less harm done to it by the succeeding device in the chain that actually records the signal.
I was in the broadcast industry for years. I'm very sensitive to sort of being abused. Somebody saying, blowing into a microphone and saying, does this thing work? They tap on it. So my question is, how robust is this equipment in terms of being able to handle that overload, as it's just part of the signal? It's resistance to overload, and if the electronics does become overloaded, how quickly does it recover and get back to sending you a good signal?
Oh, that's a really good question. And I think the answer to that lies in the term headroom. If you're going to blow into or bang your microphone on the table, you don't want your circuit to ring. In fact, if I had known that question was coming, I would have included a graph in the presentation that I ran on the tube preamps, where it gets back to the parafeed topology. If you load a tube with an inductor, it recovers immediately, absolutely immediately. There is no ringing. If you load it resistively, you're going to get a little bit more ringing. And I've demonstrated that by comparing the circuits. But the answer is very quickly, and I think that's very important. You have to design so that any bad data, any ugly signal coming into the device is not going to throw it out of equilibrium. And so headroom is the main way that I try and accomplish that. So I appreciate the question. Anyway, this is the little device that does fit in the palm of your hand. We've talked about some of this, but here it is in the palm of my hand. I have a really good friend who plays bass for Nile Rodgers and Chic, and he was a professor at the Berklee School of Music. And he was using my tube gear and he said, yeah, it's great, but no kid today is ever going to buy that. They want something that'll fit in their backpack. They want a MacBook Pro, an Apollo interface, which is a little bigger than this, and then preamp or something that can actually just fit in the backpack and create great sound in a hotel room. And using this, I know that several major artists now have recorded their vocals in a hotel room. So the idea was to do that and also make it accessible to young people so that we didn't lose my vision of what doing it right is in young people just because substitute techniques exist in their laptop. I would analogize it a little bit to writing your own stuff or using AI to write your stuff. There is some benefit to actually doing this as a human being, and I think these analog products underscore that. Obviously, tubes are impractical for that, even though I think they do something that transistors can never do. But in fairness, transistors do something that tubes can never do. The distortion signature of a transistor properly implemented sounds like butter. It's very rich and thick and magnetic. A properly implemented tube sounds like reality to me. And both of those have their place. I'm not being a tube snob here. Only thing that I want to emphasize is the color control, which allows you to blend in harmonic distortion to taste. And what I find, I think what a lot of the users have found, is that our natural inclination when we're sculpting a sound is to reach for the traditional tools like EQ, filters, to shape the sound to be something that's unique to the production. Unfortunately, that comes with all sorts of penalties. It comes with phase penalties, distortion penalties, headroom penalties, and ultimately you're using a mixer to mix all the bands of EQ back together. And the moment you engage in EQ, you have put your signal through 3 times as much circuitry as it was going through before you engaged the EQ. By dialing in harmonic distortion, you can often take away your feeling that you need an EQ. The signal suddenly sounds the way you want it to sound without chasing it through frequency bands. And the beauty of the distortion is that it operates across the spectrum. That's the feature that every single device I make and sell has, is variable harmonic distortion. I'm going to play something for you just to give you an idea of what I'm talking about. This is a video that we made at Blackbird Studios in Nashville, and we had a studio drummer with a simple 4-mic setup, and we plugged those microphones into a $1 million Neve console. If you've ever watched the movie Sound City, that's a Dave Grohl documentary, sort of an ode to the Neve consoles. Magical device. A single preamp stripped out of one of those consoles will run you about $8,000 now. We also ran it into an API mic pre, which was, if you think of Fleetwood Mac's Rumors, that's sort of sonic territory, that's API, and then ran it into a product I sell called the Swarm, which is just 4 Hornets in a box. I think you will find that they all have different signatures. I'd be curious for your reaction. So if you'll indulge me for, about a minute and a half, I will let you hear what this does on a drum set. This is the $1 million Neve. Okay, now before I move on to the next one, let me just say that one of the most important design attributes of the Neve is it uses a large power transistor at the output to drive a gapped transformer in a single-ended configuration. That is one of the time-honored ways of creating second harmonics, and Neve does it beautifully. I use a different approach, but that is a second harmonic generation tactic. API goes entirely in the opposite direction and uses what are called discrete op amps, actual operational amplifiers made out of discrete components, to go fully differential as opposed to single-ended, and it sounds entirely different. Hopefully you were able to hear some difference there. The Neve sounds rounder, mellower, a little warmer. The API is a little bit more clinical. Now the sound produced by the Hornet, it occupies a design space in between the two units. So the idea there is you're definitely descending the price ladder, but I think doing it in a way that occupies the same space as those other design approaches.
I wanted to offer my opinion on the three sounds. So I thought that the Swarm sounded the most balanced and still had the warmth of the kick drum, bass drum. I could hear the headroom in the mic pre on the top end, especially on the transients of the snare hits and the cymbal crashes. I thought that the API was definitely mid-range forward, around mostly in the snare hits. That pushes that snare forward. Bass drums were a little lacking compared to the Hornet and the Neve. And of course, the Neve low end is in the kick drum and the lower octave of the snare drum. And that's the distortion and the output transformer on the Neves, I believe.
Yeah, that gapped transformer that Neve used, which is unobtainium now, did have a certain magic to it. There's no question. But if you're going to put some serious DC current through a transformer, you have to have it gapped just right. And it is really hard to get good, consistent gapped transformers today. And you made my day by talking about the headroom and the clarity in the top end of the Hornet/Swarm. That is what I was trying to do. If you put any of these amps on a frequency response plot, you will see the frequency response on all these things will be flat within -1 dB from about 20 hertz to 30 kilohertz, no matter where you turn the color knob. But they are going to sound like entirely different boxes. As we try to describe that subjectively, we're going to say, ooh, around 10K, it's really clear and forward. We naturally translate into that, well, it must have more. But it actually doesn't. The effect of the harmonics on our listening defies measurement through a standard frequency response plot. It's really interesting to hear people who are experts in music, experts in sound, say, ooh, it sounds like there's about, something happening around 800 hertz there. Nothing's happening. It's cluing you in to a certain part of the performance that might not have been important before. I want to show you also how we actually make this stuff. In my tube preamps, I do use these Cornell film capacitors that are $6 a piece, and they look like D-cell batteries, and they sound amazing. And yes, I took a shortcut and used some X7R ceramics in the Hornet in certain places as coupling capacitors, which you're never supposed to do. But it turns out that they complement that kind of sound pretty well. And the difference, more than 100-fold in price, I think the difference might be about 0.25% in terms of listening pleasure. Transformers are bulky, they are expensive, they are unnecessary, and they sound awesome. Every microphone device I make includes input and output transformers, and the DIs I make don't want input transformers because they can't deliver the high impedances you want, but they also contain output transformers transformers, because there is a certain subjective magic to anything magnetic. I don't care whether it's tape, a phono cartridge. What magnetics do to sound is they basically mess it up. They do not convey the phase accurately of different frequencies. And yet, if you listen to a signal recorded through a transformerless input and a transformered input, I promise you that 9 or more times out of 10, you're going to prefer the one that went through a transformer. And again, this is something we don't measure very well. We can measure the hysteresis of a transformer and certain characteristics, but the way the psychoacoustic effect of what we're doing with these signals is not something that goes into the mathematics that govern the electronics. Psychoacoustics, if it's a science at all, it's not a very well-developed science, and there are very few measurements available. So we sort of have to just go on experience and take our best shot with the topologies that have worked in the past to try and synthesize something that's going to be magic. So very much against my own financial interest. The most expensive part of a Hornet is right here, the input transformer. And if I took this part out, disconnected pin 3 of the XLR and put pin 2 right into my first stage, I'd get sound. I'd get the same amount of gain. It just wouldn't sound as good. So I lose almost $20 a unit just to have that transformer in there. I will confess that even though these are discrete single-ended circuits for the most part, what I call gain cells, I do use an op-amp. I don't know how many of you are familiar with this series by TI. The 454 is sort of the lowest voltage model, but it still can handle a 100-volt power supply. A heck of a lot of power to drive a much heavier load than most output devices can. So I use that at the end for current gain to really drive the transformer. I think the purists would probably tell me that I'm screwing up by doing that Rupert Neve used a single-ended stage at the end. But he had the benefit of gap transformer manufacturing that we don't have today.
I use condenser microphones a lot. They need power, phantom power, and that's usually done with the center tap on the input transformer, reference to ground. Maybe yours is different.
It can be done that way, but what I'm doing is the same thing that people do when they're using transformerless inputs, which is to say I take the 48 volts through a pair of 6.8K resistors onto pins 2 and 3 of the signal, just impress it on that way. And that way my transformer is seeing 0 differential voltage and everybody's happy. It truly is a phantom. As a matter of fact, not one of the transformers I use for any purpose has a center tap. And center taps are great if you're going to do a push-pull amplifier, but I don't. Somebody once won an Energy Star rating for an alarm clock that was powered by gasoline. I like to think that my circuits are about as efficient as a gasoline-powered alarm clock. They use far more power than they need to, but hopefully to good effect, and we're not talking about more than a couple watts anyway. Up until about 10 years ago, I thought DIs were the least sexy thing in a recording studio, and now more than half of my business is making DIs that I think are incredibly sexy. The DI input on this thing bypasses the input transformer for impedance reasons and uses a discrete JFET to start the ball rolling. But I limit the input impedance on these devices to 100 kiloohms for noise reasons. With the tube stuff, I can go up into the tens of megohms because I've got a lot more room to play with power supply electronics to keep that clean and keep the noise out. The schematics, this little chip here is our LM3916 from the 80s. That's still the best way to do a cheap meter. Our layout software then takes that schematic and allows me to drop the components onto graphical interface that be used to generate the files needed to etch the circuit boards. Also then tells the pick and place machine that this is exactly where these components are going to go. These are all the LEDs for the meter, for example. This is the power supply filtration. And then you have actual photographs of what it looks like. Very simple. Just 2 knobs, gain and color, and 2 buttons, input switching, and phantom power. In the rack mount version, I do all the standard stuff, the high pass filters, the pads, but there wasn't room to do that in the Hornet. There's another debate about bipolar versus single-ended power supplies. I don't know how people feel about that, but in my case, I don't have any orthodoxy. In this case, the only op-amp in the circuit is run off a single-ended power supply with a virtual ground system, and that's done for cost considerations. I use the 48-volt wall wart because I can get my phantom power out of that and then just drop all the voltages from there rather than having to boost any voltages internally. All of that is purely a cost consideration, but I do find that the 454 sounds great with a single-ended power supply. I make other products that use bipolar power supplies for the op amps, so I don't think there's any magic there as long as the single-ended power supply is done properly and the virtual ground is sufficiently bypassed. What you're going to see when we go out to the pick-and-place machine is actually not a Hornet, but a board that I'm making I designed with another company that makes microphones specifically for kick drums, and it's an active dynamic microphone powered by phantom power. When you're doing that and you have very, very little power, you got 8 milliamps to work with if you're lucky for the entire device, a single-ended supply becomes virtually essential to use for the op amps. So if anybody has any questions before we move on.
In the very beginning, you mentioned about crossover distortion. When you have push-pull, I happen to have very good observation about that. When you're dealing with analog video, a multi-burst signal, if you have push-pull, you could see transition between the colors are not smooth. Switched it to a straight one emitter follower amplifier and everything was perfect. How does it manifest in audio when you have crossover distortion? How do you experience that?
And the most extreme example I can give is Fender guitar amplifier that has slightly mismatched tubes. What you experience is a very, very harsh, almost ring type sound, and also ghost notes. You might play a note that's a root and a fifth, but you'll hear some other note in there that doesn't belong, that the amplifier is actually creating. Both of those, the ring modulation sound and the ghost notes, are examples of how crossover distortion can get in your way. It's a very unpleasant, it creates ear fatigue. Now, I will tell you, that's not a slam on differential designs. Macintosh power amplifiers are all differential and they sound beautiful. It can be done well, but it is a risk differential design that you wind up with crossover distortion, just like it is a risk of single-ended design that you have no power supply noise rejection. Everything in the power supply is going right into your output. If you look at the power supply of a typical differential amp in audio, it's horrible. The ripple is disgusting, but you never hear it because it gets canceled out by the circuit. But you take huge risks along with that. So it's really interesting to hear that crossover distortion was creating those visible artifacts in analog video. I had never really thought about that. So you're saying that you took an emitter follower.
A lot of current, waste of energy, but at the end of the day, it solved the problem. You didn't see those distortions anymore.
And what was driving them?
A video op amp, high frequency video op amp. Eventually, we found something that built-in emitter follower that also needed an external resistor because the chip could not handle it. Both of them were video amplifiers, make it drive 75 ohm video. That was the challenge. If you were dealing with, let's say, 1K or 5K load, that problem didn't exist. But since the standard video was 75 ohm, that was the issue. Their follower fixed the problem.
One of the things that really strikes me about transistors versus tubes, and by transistors I'm including the active elements in op amps on chips, is the consistency of tubes is far, far better than that of transistors. You wouldn't think so because a tube is like a little handmade sculpture, and yet you can grade tubes and they retain their characteristics much more consistently than solid-state electronics, which are highly temperature dependent and have massive tolerances built in. I think that's why you get crossover distortion even in a high-quality chip when you're trying to drive a heavy load, starting to see asymmetries. And it's also why negative feedback is such a big design consideration with solid-state electronics, because it tends to mitigate the effect of tolerances in the parts.
It makes sense, by the way, because tubes are repeatable mechanical structures, whereas transistors, the doping, that are a lot of statistical factors affects the doping of the transistors and their gain, and the concentrations of the dopings might be different from one batch to the other. Totally makes sense to me, yeah.
If you put a transistor on a basic meter and measure the beta of the transistor, take 10 transistors out of the same bin and you're going to see a range of betas. It's almost 100% difference. And the doping is microscopic. Not surprising to me that there are going to be some variations. In digital, we can pretty much forget about that because of the way we use those transistors. But in analog, it's a big deal. And so you find that designers rely a lot on negative feedback to make things consistent. And of course, negative feedback, mathematically, it will tell you it reduces noise, it reduces distortion, it increases bandwidth. It's awesome. It just reduces a little gain, and gain is cheap. So why not use tons of negative feedback? Phase. When you use lots of negative feedback, there are subtle phase variations that suck the life out of the signal. And yes, the specs often get better. You do get less distortion because you're feeding that distortion out of phase right back into the input. You do get lower noise, but a significant cost from an audio standpoint. There are other applications for which negative feedback is absolutely brilliant and poses no problems at all. But you lose a lot of the subtleties, a lot of the transients when you introduce negative feedback into any audio circuit. So I'm not going to say I don't use it. I do use it, but I use very little of it, and I use it with very, very intentionally only where it's absolutely necessary. But normally I just prefer to let the devices let their flags fly, and for that reason, my way of getting consistency is biasing them and configuring them so that I'm not asking for too much gain out of any single stage. I'd rather have cascaded gain stages that do modest work with no negative feedback than these massive gains that are possible. I mean, the 17-cent op amp will give you 100 dB of gain. Won't be very stable, but it'll certainly get you 50 or 60 or almost for free, but at the cost of massive negative feedback. Those are sort of design preferences, I will say, that I advocate for. I'm not going to say that people who do it the other way are wrong, but they do create different results. If you want really awesome specs, don't buy my stuff. I don't design to specifications. I design to smiles. If you want to make a singer feel like they're singing at Carnegie Hall, then I think I've got something to offer. And by the way, Carnegie Hall isn't the best sounding room from a technical standpoint. It's just a great sounding room from a psychoacoustic standpoint. Both of the output transformers in this device, by the way, are 1-to-1 ratios. In the tube world, it actually makes sense to use a step-up transformer to get some free passive gain and a step-down transformer because small signal tubes are notoriously weak in terms of the power they can deliver. With solid state, you've got a little bit more robustness to work with, and so I've found that using the 1-to-1 ratios actually sounded better. Let the transistors do what they do and keep the transformer from imposing any more load on the signal than it needed to. And we've talked about the humbucking transformer, having the two coils wired out of phase with one another so that you actually cancel out the environmental noise. That was just essential, and that was a hard lesson learned. Another hard lesson learned, these switches here, these little push-button switches by C&K that I think I pay about $1 for. That was also unfortunate because when I set out to build the Hornet, I built it around some switches that I could get from Asia that cost 6 cents. Unfortunately, they failed after about 10 uses, and so I had to get some more robust switches. And between my humbucking transformer and my more expensive switches, suddenly my cost model kind of fell apart. The industry standard, at least in the audio industry, is that your parts cost should be 10 to 20% of retail. By that measure, I'm a complete failure. My parts costs are much higher than that. Using the wall wart does allow me to keep all of that ugly switching noise outside the unit. It's not to say that there aren't conducted emissions inside that have to be dealt with, but it mitigates the problem of using a switching power supply. You've seen before on other slides that the device runs single-ended at a little over 38 volts. There's no audio signal short of driving a PA system that is going to require more headroom than that. As a matter of fact, the Neve system uses 24 volts and still has awesome headroom. It's when you get down to 15 that you start having the problems associated with mid-level prosumer type sound.
On your wall wart, it delivers the power to your sound module by cable, right?
Yeah.
Is that cable RFI proofed? Does it have ferrite beads on it? Is it susceptible to RF? If I was to take it to an AM broadcast station and stick it in the studio that's next to the transmitter, what happens?
I've never done that precise experiment, but The candid answer to your question is there is no ferrite bead. It is not RF suppressed other than what's in the wallboard itself. I'll be honest, I spent about $4 a pop on those. Reducing that expense was one of the ways I can sell something that sounds like this for $300. There might be a potential vulnerability there, but I can tell you that in no circumstance, either that I've measured with test equipment or experienced in the field, has it been an issue. It is, I suppose, possible that if you take an unshielded wall wart and put it next to a sensitive element of a AM transmitter, you're going to get some kind of problem, but I haven't been able to do it yet, and I've measured it around RF equipment, anything I could do to make sure that I wasn't inadvertently creating an illegal ham radio. It just hasn't been an issue.
I've had problems with the PA system in a church that's in Massapequa, Long Island, that was coming from a radio station whose transmitter was in Baldwin. That distance is about 15 miles away.
Wow.
So, yeah. Those problems really do exist. I'm a ham radio operator, and I know firsthand about all kinds of stuff that happens when you get high-power RF next to audio equipment, and most audio equipment flunks miserably.
There's a certain amount of voodoo to EMC, and there's some trial and error there. My trial and error so far, I've just been lucky, knock on wood, but you're right. Those can be real problems. I will tell you that when I was first developing the first tube pre I did, I saw on the scope this gorgeous, strong sine wave. When you're working with analog, use an analog scope. When you're working with digital, use a digital scope. There are subtleties to the analog scope that the digital scope just sort of washes away. And I saw a wave that just made my heart sing until I realized it was at 3 megahertz. I had created a ham radio unlawfully. That was a design and layout of high impedance circuits long ago in my life. For this product, it was very important to me to have everything on one PCB. All of my other products use multiple PCBs with the ribbon cables or individual wires connecting the boards up. That isn't feasible when you're trying to reduce the amount of time that your hands have to spend on the device. So everything had to be on one PCB and everything had to be as much surface mount as possible. On this board, there are 143 surface mount components. It doesn't look like it when you look at the board, but there are 143 components. If I had to solder all those by hand, if they were through hole, you can imagine we're talking about at least 300 solder joints I have to do. These are 300 solder joints I don't have to do by hand. My oven will do for me. That is one of the beauties of SMT. And for those who aren't familiar with SMT, I'm at least going to show you the equipment and how that process works of mass producing with SMT, and I can do it right here in the house. This machine that you're looking at on the screen is the Neoden 10. If you don't know SMT, it's difficult to make these specs make sense. If you do, they may be too basic for you. But what I'm going to tell you is that an 0201 component, that's a size specification for SMT. An 0201 would be smaller than a flake of pepper that you would pour out of a dispenser at a restaurant. It's just almost invisible. It's crazy. The sizes go up from there to where you can sort of work with them with the tweezers. Some are big enough to use with your thumb and forefinger, but the idea behind SMT is miniaturization. A part that might once have been 1/4 to 1/2 an inch long and maybe 1/8 of an inch wide can be boiled down to something that is about the size of a piece of pepper, and it's pretty amazing. And that has the effect of reducing cost dramatically. If you had to build a laptop with through-hole components, you'd need a much, much bigger lap. It would not work. I think if I put this into through-hole components and built it 70s style, it would almost certainly be the size of a large dinner plate, not be possible to make it in that form factor. By using SMT, I'm not losing anything of the analog purity. I'm just using modern versions of the same components. And I should say that I think the manufacturers today are putting more effort into the quality of their surface mount components than they are a lot of the through-hole components. There's another incentive to use them. Tolerances are crazy low compared to through-hole components, especially for the price. Solid-state devices are vanishingly cheap. It's a really great development in manufacturing. I mean, I will say that we occupy a price point that is basically unique. There is no way to do this anywhere near the price of these machines. There are beautiful, amazing machines that cost millions of dollars out there and do incredible stuff. But if you want to get boards out the door in a cost-effective way, it's really pretty hard to beat this. I started with my little desktop model, the Neoden 4. It would get boards out at a reasonable speed, but it had some significant limitations, like it couldn't handle parts that were taller than 5 millimeters. So goodbye electrolytic capacitors and mechanical relays and things like that. Pretty serious constraints. With the machine I'm using now, there's no component I can't place. I feel sort of liberated as a designer. I don't have to design to the machine. I design to the product, and that's pretty nice. Abstractly, before we go into the actual room with the machine, I will just tell you that the steps are outlined here. You start with a bare PCB. I like to use PCBs with an OSP finish. They're very, very flat, but not as expensive as the gold finish. And through a stencil, you apply solder paste. Solder paste itself is a whole long class on solder paste because of the European RoHS regulations that prevent us from using the tin lead stuff that I grew up with. Still legal in the United States, but not legal in most countries, so we have to get away from that. The standard is something called SAC 305, which is a copper, tin, silver alloy, melts at a very, very high temperature, perilously close to the temperatures that destroy components and all sorts of other problems. Fortunately, there's another chemical element that comes to the rescue, bismuth. If you use a tin bismuth silver alloy, you can actually get the paste to melt at 138 C, which is really, really low and poses no threat at all to your components as they go through the oven, and also makes reworking a whole lot easier. So we use bismuth paste applied with a semi-automatic wiper that I'll show you that wipes the paste across the stencil, depositing it just on the pads. Put that into the pick and place machine and all your parts are placed. I have a little oven that you'll see actually runs on 110. It takes only 1800 watts at its peak power consumption, but is a 6-zone oven, enough to give you a nice precise reflow profile. And then when that drops out of the other end of the oven, you've got a board that is SMT'd, but still needs its through-hole components to become a final product. The design goal is to make those through-hole components as few as possible. Where you find that you cannot get away from them, usually large electrolytic capacitors that are either really high voltage or really high capacity, can be hard to do with surface mount. And then jacks and pots and switches, generally speaking, need to be through hole because the mechanical components have a hard time with the heat of the oven. That's the basic process we're going to look at. Anybody want to ask anything about that before I go out and show you the machinery?
Things like jacks or potentiometers or something for adjusting tone or volume or something like that require some user input, and they need some flexibility there. I've seen these things where they actually crack the circuit boards because they're very rigid and brittle. What kind of solution do you have for that?
As through-hole components or SMT?
SMT.
In fairness, one of the disadvantages of the bismuth paste that I love so much is it can be certainly more brittle than the tin lead, and that is an issue. To my mind, if you're going to make a reliable product that has potentiometers, push buttons that are mechanical, not just membranes, or jacks or switches, you really ought to be doing that through hole. There are ways to do them through surface mount, but I have not found a way that I feel comfortable that they're reliable for exactly the reasons that you say. Through hole is the way to go for those, I think. One of the other things about surface mount that's kind of a contradiction in terms, pick and place machines are crazy precise. You can place accurately to within 1/100th of a millimeter. Using advanced vision systems that measure components on the fly, you can correct for angular errors. It's amazing. But at the end of the day, when the component is placed and baked in the oven, there's a lot more wiggle room than you'd imagine. Components, they look reasonably straight, but they can be a little bit off because there's nothing mechanical holding them in place until the solder has melted and cooled. Otherwise, they're just held in place by the tackiness of the flux. And so you can wind up with some, especially rotational errors. If you try to do that with parts that have to protrude through holes in an enclosure, for example, you can find yourself with finish problems also. So I try to stay away from surface mount components that are going to be touched by the user. I love surface mount, but it has its limitations. And good old-fashioned through-hole is, I think, the way to go for fit and finish and for anything mechanical that might require a lot of hands touching it. I'll admit I have experimented with some board-to-wire connectors that are surface mount, and while there is a cost benefit and there is a speed benefit to them, I don't like them. And I will probably move away from them in later iterations of my board because they don't do as good a job of gripping onto wires as components that don't have to go through an oven. And I'm using very high quality ones, but surface mount has its place. And then there are times when through hole is still the way to go. If you're making a remote control, for example, for a TV, there's not really any reason to use through hole. But if you're using something where there's going to be any sort of shear forces, angular forces, or, God forbid, mechanical elements that affect the electrical performance, like the wiper on a potentiometer, you're much better off just biting the bullet and going through hole, get better reliability. That's my take, at least. We are now going to go mobile. As an example, I was telling you about that active dynamic mic we're building right now, and we're going to make several hundred of these boards, so it's set up for these, but the boards come on panels. Each one of these circles is a product. You can see what looks like bare copper on the pads. That is the OSP finish, which is an organic finish that disappears in the oven, has a limited shelf life, but it protects the copper and leaves it very, very flat, so you get good placement of small, sensitive components. We put that on a bed here, like that, right? And have these little pins to hold it up so it's flat. The stencil has holes precisely for each pad. And then when we lower that stencil, you can see the copper pads show up through it. Formerly in production right now, we'd have paste here and these wipers would wipe it across. That's the application of the solder paste. Simple as that. This is the Neoden 10 pick and place machine. So I'm assuming I had the solder on here. Put the board on these rails, advance it into the machine. It's then clamped onto the rails, so it's nice and solid, not going to go anywhere. And as you can see, with all of the components here, are on these reels that have thousands and thousands of components on these tapes. This machine can handle 66 different reels for 66 unique components. I mean, they can be any size. For example, these are those wire-to-board connectors I was talking about that are big enough to place with your teeth. And then you've got these 0603 resistors in this case that are very, very small and have to be picked up with a nozzle that has an opening of only 0.4 millimeters. This will give you a better idea. The machine has 8 different nozzles that can be of different sizes so that they can work with different components. Then the whole head is driven by a ball screw mechanism with servo motors, and very, very, very precise and very fast. When we get this thing really up and running, it is completely feasible in the real world to do 10,000 components per hour, although the specs might be higher than that. There's a lot of art to setting a system like this up. There's a lot of optimization that has to happen so the head makes as few trips as possible and moves between feeders as efficiently as possible. These are Hornets as they come out of the machine with no through-hole components. 2 complete units with all the placements done come out of the machine. Had it not been baked, if I did this, they would all just fall right off onto the floor, but they have been baked once it comes out of here. That's the whole oven. You can see it has adjustable tracks for different width PCBs. If you look at the screen, I've got a profile here with top and bottom zones. What's it taking right now? 7 minutes and 8 seconds from start to finish to run the board through all of these different temperatures. These temperatures are the temperatures of the plates over the board and under the board, not the board itself. So they're a little higher than you would actually want to see on the board. A profile like this will get you perfect solder every time using this bismuth paste. If you wanted to use SAC 305, you could. You just jack everything up by 50C. With something functional, but might be actually kind of ugly. I can show you the difference there. This board is SAC 305, and you can see that the solder is gray. It is just less precise. There's extra solder pellets that have boiled off because of the extreme heat required. Whereas this one, the solder is more shiny. It looks more like tin lead solder, and there's no excess flying around causing potential problems. So I'm a big believer in bismuth paste, even though it's a little bit more expensive. That is the process we use. Let me go back so I can be on the screen. That was a quick overview. If anybody wants to see these things in operation, I'm happy to do a video call and show you, but there are a few ways to make a presentation bad more effectively than somebody, playing with a mouse and clicking through various screens, optimize a board that you don't care about. So I've tried to condense that process to be descriptive only, but I'm happy to show you anything you want. Are there any questions at this point? Well, let's start with the stencil printer. The one I just showed you is a pneumatic semi-automatic one that is pretty awesome and gives you very nice consistent results. But honestly, until 2024, I was using a manual one, which is basically a hinged holder for the stencil that lowers down on the board, which is held in place with those pins. And then you swipe, just like you were making a t-shirt in 6th grade. You just swipe the paste across with a manual knife. That works fine, and that is one area where I think you can scrimp. The oven, I would say, whatever oven you buy a conveyor oven. Don't buy a drawer-style oven. I don't care what they say. I don't care how well made it is or how reputable the brand is. They are inherently bad. They can't achieve temperature changes rapidly enough to match the profile. They don't distribute heat as evenly as possible, even if they have fans and fancy controllers. So, for me, the quality, the yield that I got after I moved from a drawer-style oven to a conveyor-style oven was night and day, absolutely night and day. So you definitely want to have a belt for your boards. As far as the machine goes, the pick and place machine, it depends on what your components are like and how many boards you're going to produce. We have a machine called the YY1 that, I don't know, it's about $4,000 retail that will do a very nice job of making boards with fairly small standard components. It only has 2 nozzles. It does have a nozzle changer, which is kind of cool, but uses pins to drag the tape in the feeders instead of actual active feeders. So there are all sorts of compromises there, but it will make some nice boards for you as long as your parts aren't too large and too demanding. If you're doing a lot with, say, electrolytic caps or relays that are big and thick and on tapes, that's when you kind of need to move up to the next level of machine. The feeders that you saw that were holding those reels on my machine are pneumatic. And they are basically just clones of the Yamaha feeders that you can get very, very cheap, standard 8mm feeders, less than $100. And they run on compressed air. They're dumb and they're reliable as all get out. They have absolutely no intelligence at all. They don't pretend to. They don't take inventory of your parts. They're not adjustable on the fly. The only way to adjust them is to get out your Allen wrench and move shims around. But man, once you have it set, it's going to place, a million components without making an error. And they come in enough different shapes and sizes that they can accommodate any part. The machine I showed you has the option to use electric feeders. I typically don't, because the pneumatic feeders are just so reliable. If you get an SMTech machine with dual electric feeders, they're awesome. They work very, very well, but populating one of those with feeders will cost you between $300,000 and $400,000, which is a little bit over my budget for feeders. The sweet spot, I think, if you have demanding components, is the pneumatic feeders and a machine that can take them. And if you have fairly standard components that you don't need high volume, you can use trays for your chips, things like that, then you can afford to really drop down the size and cost of pick and place machine you use. But definitely the place not to skimp is the oven, because it doesn't matter how well your components are placed if they're going to get soldered badly. With a through-hole assembly, you can determine whether there's a cold joint, a flaw pretty easily just by looking at it. That's really hard to do with SMT. Really hard to do. And if you've got a bad solder joint on a board that might have, 300 solder joints, chasing that down just took away the entire advantage of using SMT in the first place. So oven first, everything else second. I guess that would be my answer. I do use two companies. One is American and one's Chinese. And the Chinese honestly do a better job. What I do is I take the whole zip PCB layout software program produces, and I send them either to Advanced PCB in the US, which is great at doing really, really fast turnarounds. The prices are really high. It's like $33 for a board, but you can get it in 2 or 3 days. And that's great for prototyping. You don't have much flexibility with that company over what those boards consist of. You get 1 ounce copper, green solder mask, 2 layers. That's pretty much it. If you want to do anything like 4 layers or more, or you want to do different finishes, you're looking at some pretty significant delays, and then the cost really can't be justified over what China can do. I use a company called PCB Win, not PCB Way. Similar names and similar websites, but PCB Win is the original Chinese company that you actually deal with a human being, not just a website. I work with Beatrice in case anybody wants to use them. She will take my files, keeps a running list of every board I've ever done, so I can just order up replacements very quickly. And, their production time for a 2-layer board can be as fast as 3 days, and then you've just got 3 or 4 days for shipping. If you're doing 4-layer plus, that processing time takes 8 to 10 days. The price of those boards is really, really low, and the quality is excellent. I've had quality problems with Advanced PCB. Also, Advanced PCB can't make you a stencil, which means I have spent plenty of time during sort of intense prototyping phases, getting ready for a trade show or something, where I'm cutting my own stencils out of overhead transparency film on a laser cutter and then, taping it to the board and trying to smear paste on with a razor blade. It just does not give you a very good result or very good feeling. So my preferred way to work is to get the framed stencil and the boards made by PCB Win. If I had another 60 years in front of me, what would I study? That is an awesome question. I would probably do what my daughter did and study neuroscience. I would certainly have more formal training in electronics than I do. I would like to have that formal training. Because I'm so focused on audio and creating an experience for a listener that really can't be described in technical terms very well, I would like to know more about the psychoacoustics. I would like to know more about the way the brain is processing the signals that I'm helping to generate. I would spend my time, my educational time, if not exclusively, much, much more heavily weighted to the sciences. I don't think I would do all electrical engineering. There's just so much beyond what one can learn in a lifetime. I'd devote some resources to that. When you think about unique components, there are green LEDs, yellow LEDs, red LEDs, those are unique components. I try as best I can to use either the same component values as much as possible. If I need a 20K resistor, use 2 10Ks so I don't have to use an extra reel, things like that. With the 10 that I showed you, having 66 unique components, you can do a lot with 66 unique components. If you're using components that are large, like a relay, for example, that reel might wind up taking the space of 2 or 3 other components. So saying you have 66 slots, it's true, but if you're going to use really big components, you might wind up with fewer than that because they occupy more real estate on the machine. I think there are 49 unique components, and some might be used 11 or 12 times. Some might only be used once. I probably have a dozen BC846Cs on here, and I use them both for audio and part of it for power supply filtering. A whole slew of 10 microfarad, 50 volt X7R capacitors, tons of those. And then, only one 454A op amp. It's always fun to try and design to use the same component as much as possible. I find that a game that I enjoy. Well, no, you can, but I don't. And the reason I don't is actually gets back to good old Rupert Neve. After his glory days in the 70s when he was building those consoles, in the 90s, he built some rack mount units for a company called AMEC. And I bought one. And I replaced the tantalum capacitors and the power transformer, the toroid, that it dragged down about 5 times because the failure mode of tantalum capacitors is typically actually closed, whereas the failure mode of standard aluminum electrolytics is open. Having a short circuit that could pop up at any moment just scares me. And since I started as a tube designer and working with much higher voltages, it scared me even more. So I avoid tantalums as a matter of personal preference for that reason. But Rupert used to love tantalums, and as coupling capacitors, if you bias them right, they can actually have a very cool sound. It's just the reliability factor and the possibility of a cascading failure. The electrolytic will fail usually as an open circuit. If the tantalum fails, amazingly on the Neve I had, the tantalums would fail and they wouldn't burn PCB traces, but they would completely smoke a toroidal transformer. I grew to have sort of a negative feeling about tantalums. That's not to say that there aren't places where they're warranted, but aluminum electrolytics are also cheaper. And as I admitted earlier, on the Hornet, I do make some cost-conscious capacitor selections. We had more time, I'd run and get one of the boards for one of the tube pre's, and you would see the capacitors are much more expensive and exotic on those. Also, I should point out that the products I make for bass guitar, I've taken to using bipolar electrolytics. Including me. There's nobody who's going to tell you that that's always a good idea to use ceramic in audio. But there are places where they can be used very effectively, and a lot of it depends on the kind of ceramic capacitor you're using. Back in the through-hole days, I wasn't a student of ceramic capacitors. I don't know all the types that were available. But today, the dielectrics you can get in surface mount ceramics are very, very widely varied. And so the only two types I use are the COG and the X7R. I don't go down to the X5R or anything like that. In the spec sheets, you'll see those mainly as being affected by temperature, and there can be some dramatic temperature effects on the performance of those capacitors. Also, DC bias can affect them much more than you'd want if you're not careful. There are also times when they sound good, they're space effective, cost effective, and they make a ton of sense. I have never had a situation where I could hear the piezoelectric effect as an input. In other words, piezoelectric effects never came out of the output of my devices from ceramic capacitors. However, I have had experiences where they themselves create sound by piezoelectric effect, where they can be output devices. That's really unsettling, I admit. I'm aware of that problem, and I don't swear by the use of ceramics for every application, but I'll tell you, there are plenty of applications. You know, they have advantages, too, for a lot of applications. I've used air quotes here, but they are faster than electrolytics. Very, very common technique is to take a high-value electrolytic and bypass it with a small ceramic to cover the spectrum. The problems exist, but I think they get a bad rap. Just like the problems exist with tantalums, and I probably give tantalums too much of a bad rap. I remember the moment where I tried a ceramic audio coupling capacitor on the Hornet in a certain location that I had not intended to use it, and I was so pleased with the way it sounded that I just went with it.
I'd like to thank Peter for a fantastic presentation. Learned quite a bit about the whole design process that you used, all those trade-offs you had to make. I think we all have a better understanding of the manufacturing as well. Thanks again, Peter.
I really enjoyed talking to you all. Thank you.
Okay, professional engineers, it's safe to go.